welcome to this calculus video for Chapter 8, Section 2, the section on L'Hopital's rule. Now, before we get started on L'Hopital's rule, I want you to pause for just a second and try the following three warm-up problems. I'd like you to simplify these complex fractions. All right, let's go over the solutions here. 1 divided by 1/25 is in fact just equal to 25. That should have been pretty easy for you. 1 divided by 1 over x, if we flip and multiply, that's multiplied by the reciprocal of 1 over x. That's 1 times x over 1. So again, this simplifies to simply x. And sine of x divided by 1 over x can simplify to x times sine of x. Now we'll see in a little while why these kind of simplifications, or sort of working these kind of problems in reverse, might come in handy in certain circumstances for L'Hopital's rule. So L'Hopital's rule, named after Guillaume de L'Hopital. You can see a photo of him here. No, not a photo. 1661 to 1704, so long before photos were invented. So, of course, this is a portrait of L'Hopital, styling very fashionable hairdo of the time. And, of course, L'Hopital did not invent L'Hopital's rule. Sorry. Actually, L'Hopital's rule was developed by his teacher, Johann Bernoulli. One of the Bernoulli brothers, who was very prolific in math, science, and many other fields. But Bernoulli was L'Hopital's teacher, and L'Hopital paid him for private lessons and then published his book about calculus based on his lessons, and then took credit for L'Hopital's rule. So I guess we should really give credit where credit is due here. Johann Bernoulli should be credited for L'Hopital's rule, but we don't call it Bernoulli's rule, we call it L'Hopital's rule. Maybe it's just more fun to say. It slides off the tongue, L'Hopital's rule. So let's see what L'Hopital's rule is all about. Basically, L'Hopital's rule deals with limits that are in indeterminate form. So it's been a while since we did limits solely as a end in themselves. We've used limits to prove ideas about integrals. We've used limits to prove ideas about derivatives. But let's go back to actually calculating limits. Suppose I want to calculate the limit of this function as x approaches 2. Of course, we immediately run into a problem, because if we try to do direct substitution, we'll get a 0 in the denominator of this fraction. Notice, though, that we also get a 0 in the numerator of this fraction. What we call that is an indeterminate form, 0 over 0. Numerator approaches 0, denominator approaches 0. So back in Chapter 2, when we did limits, we would have approached this problem by trying to factor this, do a little bit of algebra, and see if we could cancel out that x minus 2 that was causing us the problem in the denominator. And of course, numerator factors as x plus 2, x minus 2. Now the factors of x minus 2 and the numerator and denominator can cancel, leaving us with the limit as x approaches 2 of x plus 2. Now we have no problem doing direct substitution. Plugging in the 2 in place of x, we get a limit of 4. So L'Hopital's rule takes a little bit different approach to this type of a problem, the indeterminate form. What we're looking at here is considering the numerator and denominator to be two separate functions, f of x and g of x. And the limit as x approaches 2 is really the ratio of that numerator and denominator as x approaches 2. If we look at this visually, we can see that as x approaches 2, we have the parabola x squared minus 4. We have the straight line x minus 2. As they both approach x equals 2, both approach a value of 0, but the question is, in what way do they approach that? If we were to zoom in, these curves, even the blue curve, would appear almost like a straight line. And we know from calculus that with straight lines, we can approximate their rate of change with a very small, what we call the differential. The differential of the x squared minus 4, we could call it df, or the differential of the red curve, x minus 2, we could call that dg. And as we look at that differential, as x approaches 2, really the ratio of the blue curve values to red curve values could really be thought of as the ratio of df over dg. These differentials, a very small change in x, producing a very small change in f, a very small change in x, producing a very small change in g. And df dg, if we are looking at these with respect to x, then we could say this is equal to the ratio df dx over dg dx. But that's exactly the same thing as saying the derivative of f with respect to x over the derivative of g with respect to x. Right? And L'Hopital's rule tells us that when we run into an indeterminate form such as this, we can take the derivative of the numerator, the derivative of the denominator, and try the limit again. Derivative of x squared minus 4 is 2x. Derivative of x minus 2 is 1. And now we can do the limit as x approaches 2 by direct substitution. Plug in that 2 and we get 2 times 2 over 1, or a value of 4 again. Same limit we got by the other approach of factoring and canceling, but this time we didn't have to really apply any algebra tricks. It was simply some calculus tricks, taking the derivative of the numerator, derivative of the denominator. So here's the formal rule written out. We start by the fact that the original limit needs to be indeterminate. That's an important condition. Don't try to apply L'Hopital's rule if the original limit is not indeterminate. But if limit as x approaches a of f of x over g of x is indeterminate, then the limit as x approaches a of f of x over g of x is the same thing as the limit as x approaches a of derivative of f of x over derivative of g of x. A little bit more formal proof. The visual explanation is not convincing to you. We could start this. We could start by sort of working backwards. We start by saying the derivative of f with a plugged in over derivative of g with a plugged in. This is the way we're hoping to be able to do the limit, by just simply substituting a for x in the derivative on top, substituting a for x in the derivative in the denominator. Let's see what this is equal to. This is equal to, going back to our definition of derivative, this was that alternate definition of derivative that we talked about in chapter 3. Limit as x approaches a of f of x minus f of a over x minus a. And then derivative of g is limit as x approaches a of g of x minus g of a over x minus a. Now we'll apply a few of the rules and properties of limits. One is that I can take this single limit, or these two limits, and write them as a single limit. All right, that seems like a pretty complex fraction, but in algebra we learned that we can simplify complex fractions by multiplying the numerator and denominator by the common denominator. If I multiply the numerator and denominator of this fraction times x minus a, the x minus a's will cancel, and we'll have limit as x approaches a of f of x minus f of a over g of x minus g of a. Now, the essential part of this proof is coming right now. This is where we're going to apply the condition that we talked about on the last page, that this has to start out as an indeterminate form. Well, in an indeterminate form, f of a over g of a is equal to 0 over 0, or f of a and g of a both approach 0. That's the reason we couldn't take the limit in the first place. If I plug a into f, I get 0. If I plug a into g, I get 0. So direct substitution didn't let me take that original limit. So what we've got at the very end here is the limit as x approaches a of f of x over g of x. When it's indeterminate, we can trace back these equal signs and work our way all the way back to the derivative with a plugged in over the derivative of g with a plugged in. So numerator derivative, denominator derivative, and now we try direct substitution again, and plugging in a into both cases hopefully will bring us to an answer. Here's some examples. We have limit as x approaches 0, 1 minus cosine x over x plus x squared. Direct substitution is not going to get us anywhere here. The numerator would equal 0, denominator would equal 0. However, if we take the derivative, we wind up with limit as x approaches 0 of sine of x, that's derivative of the numerator, over 1 plus 2x, that's derivative of the denominator, and now we can try direct substitution again. As x approaches 0, sine of x goes towards 0, and 1 plus 2x goes towards 1. This winds up being 0 over 1. This limit is actually 0. Notice that as soon as this is not indeterminate, we stop. We don't want to take the derivative again. If we continued to try to use L'Hopital's rule after the limit is not indeterminate, we would wind up with cosine of x over 2, and that would seem to produce an answer of 1/2. Well, the limit is not 1/2, the limit is 0. You could check that visually if you'd like. Graph 1 minus cosine x over x plus x squared. And you'll see that as x approaches 0, the entire function goes towards 0, not towards 1/2. So don't continue with L'Hopital's rule after the limit becomes no longer indeterminate. So at each stage after you've taken the derivative, make sure you try direct substitution. Try plugging in that 0 for x in both cases. And see if you get something that is an actual answer and not indeterminate anymore. All right, there are times, however, when we will want to apply L'Hopital's rule more than once. Here's an example. Limit as x approaches 0, square root of 1 plus x minus 1 minus x over 2 all over x squared. Trying to plug in 0, we get for the numerator a value of 0, for the denominator a value of 0. That is indeterminate. So let's try to take the derivative. Well, a better way of writing that numerator is 1 plus x to the half and minus 1 minus 1/2 x. That just makes it easier to do the derivative. Let's see what the derivative of the numerator over the derivative of the denominator turns out to be. Here's the derivative of the numerator. 1/2 quantity 1 plus x to the negative half minus 1/2. Derivative denominator, 2x. Unfortunately, when we try to plug in 0 for x, again, we get a value of 0 for the numerator, 0 for the denominator. It's still indeterminate form. Therefore, we can try to do L'Hopital's rule again. Let's take the derivative of the numerator again, take the derivative of the denominator again. Now we have limit as x approaches 0 of negative 1/4 quantity 1 plus x, close quantity to the negative 3/2. Denominator derivative is 2. And this, when we try to plug in 0, is not 0 over 0. The numerator is actually negative 1/4. Denominator is 2. And negative 1/4 divided by 2 gives us the number negative 1/8. So the limit of our original function is -1/8. It took us 2 rounds of L'Hopital's rule in order to reach something that was not indeterminate anymore. Now, we've been examining indeterminate form 0/0. It turns out there are some other indeterminate forms besides 0/0. Here are a few of them. These following are also considered indeterminate. So if I do a limit and I wind up with infinity over infinity, both the numerator and denominator are approaching infinity, that's also considered indeterminate, and therefore it's eligible for us to do L'Hopital's rule. Another thing we might run into is infinity times 0, and what we're talking about here is one part of the function goes toward infinity, the other part of the function goes towards 0, and we're multiplying these two factors, one going to infinity, one going to 0. Infinity minus infinity. So we have two parts of a function, both going to infinity and subtracting. Now you might think, oh, that's just 0. But if you know anything about infinities, it's not quite that simple. Infinity minus infinity could equal all kinds of things. So we'll have to apply L'Hopital's rule in a little bit different way. 2 more indeterminate forms, 3 more indeterminate forms that we'll look at is 1 to the infinity. So remember, this is a function whose limit goes to 1, and another function in the exponent whose limit goes to infinity. We could run into the indeterminate form 0 to the 0. So a function whose limit is 0 to another function whose limit is 0. And another form is infinity to the 0 power. So if the base function goes toward infinity and the exponent function goes toward 0, that's called an indeterminate form. So let's take a look at each of these other indeterminate forms and see how L'Hopital's rule tells us to deal with those. The first one, infinity over infinity, we can simply evaluate it just like 0/0, take the derivative of the numerator, derivative of the denominator, and try direct substitution again. Hopefully after enough applications of L'Hopital's rule, we'll get to a solution. But these other ones aren't even in a fraction form. Infinity times 0, infinity minus infinity, these exponential type functions, they're not in a fraction form. So these others are going to have to be changed to some sort of fraction form before we can apply L'Hopital's rule. Here's how it'll work. We have the limit as x approaches infinity of x, sine of 1/x. If we look at this and try to sort of do a direct substitution, if x goes toward infinity, of course, x goes toward infinity. But 1/x, as x approaches infinity, is approaching 0, and sine of 0 is 0. So we have this sort of tug of war happening here. One part of the function is going toward infinity, the other part is going toward 0. What's going to settle this little tug of war going on here? What we're going to do is apply L'Hopital's rule, but first we need to turn this into a fraction. Gee, I wonder what sort of fraction could take the place of x, sine of 1/x. Well, let's think back to our warm-up. Remember in our warm-up, we had some fractions that we reduced to a simpler form. Let's take a look at this fraction, sine of 1/x over 1/x. In a simplified form, isn't that the same as x, sine of 1/x? Well, it is. So our approach here is to sort of not simplify, we're complicating. So I've complicated x sine of 1/x, but I did it in such a way that now we're in a position to apply L'Hopital's rule. We have a fraction, numerator and a denominator. The numerator goes towards 0 and the denominator goes towards 0. So now we're back in familiar territory. We can apply L'Hopital's rule, do the derivative of the numerator, derivative of the denominator. Now, you might recognize this as a form of one of the limits we learned a long time ago. Limit as x approaches 0 of sine of x over x, or sine of u over u, or sine of theta over theta is 1. Well, as x approaches 0, as x approaches infinity, 1 over x is approaching 0. So these are essentially the same problems. Let's see how it works out with L'Hopital's rule. But we should be expecting an answer of 1. Let's see if it checks out. Using L'Hopital's rule, derivative of the numerator is cosine of 1 over x times, and here's the chain rule, the derivative of 1 over x, negative 1 over x squared. In the denominator, I've written the derivative of 1 over x, negative 1 over x squared. Now I can see that we can do some simplifying. These will cancel, leaving us with limit as x approaches infinity of cosine 1 over x. Now, can we apply, or can we sort of do a direct substitution? If x goes to infinity, 1 over x will approach 0, and cosine of 0 is equal to 1. Okay, that's the answer we were expecting to get based on this idea. So L'Hopital's rule can apply even if we have to sort of complicate these expressions first. If it's not already in a fraction form, we have to complicate it into a fraction form. But a fraction that could be simplified back to our original expression. Here's an example of infinity minus infinity. As x approaches 1, this first fraction approaches 1 over 0. Natural log of 1 would go towards 0. 1 over 0 means that this first fraction is approaching infinity. If x approaches 1 in the second fraction, this fraction also approaches infinity. It's the indeterminate form infinity minus infinity. Well, remember, L'Hopital's rule only can be applied if we have a single fraction. Well, the trick here is just to combine these two fractions. Find a common denominator and subtract. If you want to verify that this is the expression above written as a single fraction, find common denominators and subtract, and this is what you wind up with. Now, if we try to apply x equals 1, direct substitution, we'll get a 0 in the numerator and we get a 0 in the denominator. That's the old familiar form, indeterminate form that allows us to use L'Hopital's rule. So now let's apply L'Hopital's rule. We can take the derivative of the numerator and the derivative of the denominator. Derivative of the numerator is 1 minus 1 over x. Derivative of the denominator, let's see, make sure that you are applying here the product rule. This is u prime times v plus uv prime, so product rule in the denominator. I've done derivative of the numerator, derivative of the denominator. Now let's try plugging in 1 again. I'll get 1 minus 1 over 1, 0 in the numerator. 0 over 1 plus natural log of 1, 0 in the denominator. I got an indeterminate form again. Now, before I take the derivative a second time, applying L'Hopital's rule, again, I'm going to simplify this complex fraction. I'm going to multiply numerator and denominator times x. It'll just make the derivative a bit easier to handle. Of course, we're still in the position where we're getting 0 over 0, so it's still an indeterminate form, even in this simplified fraction form. So let's do L'Hopital's rule one more time. Derivative of numerator over derivative of denominator. Derivative of the numerator is 1. Derivative of the denominator, making sure we apply the product rule for x times natural log x, get ln of x plus x over x, and derivative of x is 1. Now let's try direct substitution one last time. Let the x equal 1. Numerator, of course, is 1. Denominator is 0 plus 1 over 1 plus 1. That's 1 over 2. And so took us a bit. It took us some simplifying of fractions. We had to simplify a complex fraction. We had to apply L'Hopital's rule twice. But we were finally able to find this limit. So it turns out in this case, infinity minus infinity equals 1/2. Finally, we're going to look at the indeterminate forms 1 to the infinity, 0 to the 0, and infinity to the 0. For any of these three forms, we're going to use a little bit of a trick. I call it the natural log trick. And we'll see what that means. So here's an example. Limit as x approaches infinity of x to the 1 over x. Well, as x approaches infinity, this base function is going toward infinity. The power function, or the exponent function, 1 over x, is going towards 0. This is this last indeterminate form, infinity to the 0 power. Well, let's remember, we can only apply L'Hopital's rule when we're faced with a fraction form that's indeterminate, 0 over 0 or infinity over infinity. This is neither one. However, we've seen before when we're solving exponentials, often it's helpful to take the natural log of something like this. Now, if I simply take the natural log, I'm changing this function quite a bit. But if I take e to the natural log of this function, I'm really not changing it at all. So e to the natural log of x to the 1 over x. I can either do the limit out in front, or I'm going to actually stick with the limit right here in the exponent. Whatever the limit of this exponent turns out to, we'll take e to that limit, and that will be our solution. So the nice thing about natural log is it lets us apply a property of logs, take the 1 over x and bring it in front of natural log. So now we're looking at this expression. We could either think of it as 1 over x times natural log of x, or natural log of x over x. And now as we look at this indeterminate form, if x goes to infinity, natural log of x goes to infinity. If x goes to infinity, x goes to infinity. This is the indeterminate form, infinity over infinity. We're finally in a position where we can apply L'Hopital's rule. That fraction form, it allows us to apply L'Hopital's rule. Derivative of natural log x is 1 over x. Derivative of 1 is 1. And the limit, as x approaches infinity, now goes to 0 over 1. But our final solution is not 0. The limit of the exponent is 0. And e to the 0 actually equals 1. So the limit of our original function turns out to be 1. Now, as you look through this example, you'll see e to a little tiny limit, e to a little tiny limit, e to a little tiny limit, e to a little tiny limit. One approach to these problems is not to try to write these in little tiny letters as you do these problems on paper. But one of the ways we sometimes do this on paper is starting with the limit of v to the u power, where v and u are functions and their limits go to either 1 to infinity, 0 to the 0, or infinity to the 0. If we get one of these indeterminate forms, look at a different limit. Look at the limit of natural log v to the u. So on the paper, we're just doing the limit of natural log v to the u. Of course, this exponent can come out in front of natural log v. write it in a fraction form and apply L'Hopital's rule like we saw in the last example, and we come out with a number. What we have to remember is don't stop with that number. Since we were taking the limit of natural log v to the u, to get the actual limit v to the u, we need to take e to this power. E to the power of that limit that you found. So our final answer is going to be e to the L power. All right, it's your turn to try some of these problems. My suggested assignment from our textbook, page 450, 1 through 47 odd and 57. You'll get to practice some basic L'Hopital's rule problems, and as you move further along, you'll find those other indeterminate forms. And your challenge is to make them into a fraction so that you can apply L'Hopital's rule. Good luck, and let me know if you have questions. Thank you.